Hello dear students, in this session let us study some more important theorems in your functional analysis. Okay, so the next theorem statement says that let B and B prime be Banach spaces and T a continuous linear map of B onto B prime, then the image of each open sphere centered at origin in B contains an open sphere centered on the origin B prime. So this part we have to prove. They have given that B and B prime are Banach spaces and T is a continuous linear map of B onto B prime. That means I can write T is a mapping from B onto B prime which is continuous and linear. Right? So we have to prove that image of each open sphere centered at origin in B contains an open sphere centered on the origin B prime. That means if I choose SR prime as an open sphere in B prime, this is contained in image of each open sphere centered at the origin in B. That means I can write that in the form of T of SR. This is what we supposed to prove. So let's see how we can prove this. Before proving this theorem, first I will construct the set for open sphere SR and SR prime. Okay. So let SR and SR prime be two open spheres, and we can observe there is no radius, the center is at origin, so centered at origin and the radius is R here. This is in B and B prime spaces respectively. So the set may be in the form of SR is equal to X belongs to B such that norm X is less than R. This is how we define our open sphere, right? You should be very careful here. Since it is an open sphere, you should write less than. It is not less than or equal to. If you write less than or equal to, it will become closed sphere. So make sure about the inequality. Okay. Similarly, let us define SR prime. X belongs to B prime such that norm X is less than R. This is how we define two open spheres in B and B prime. Now SR is equal to X belongs to B such that I can write this as norm X by R is less than 1, right? We can write in this way. So now I will consider X is equal to Ry. So if X is equal to Ry, this set becomes SR is equal to Ry belongs to B such that I can write norm X as R into norm Y divided by R, which is less than 1. Or we can write this as SR is equal to R into R is some real number, so I am taking out Y belongs to B such that norm Y is less than 1. So now if you observe this, we can write this whole term as SR, right? Sorry, I will denote this as S1 because here my radius is 1. Initially the radius was R and here the radius value is 1. When the radius is just R, we denoted that as SR. Here the radius is 1, so I will denote that as S1. So now SR is equal to R into S1, right? So this implies T of SR is equal to T of, in the place of SR I can write RS1. Since T is linear, we can write this as R into T of S1. So T of SR is equal to R into T of S1. Call this as equation number 1. We will use this in the further steps. Okay. So what is our aim? Our aim is we have to prove that T of SR is equal to, this is image of SR and it contains some SR prime. This is what I have to prove, right? In the statement they have given that the image of each open sphere centered at origin in B contains an open sphere centered on the origin B prime. So I am just writing this statement in this form. Here T of SR is nothing but image of SR contains some SR prime. That means SR prime is the open sphere in B prime. So first let's prove that T of S1 closure contains SR prime. Okay. So now for each positive integer n, I will consider an open sphere Sn in B. That means I can write B as union of all open spheres. In order to extend for T of SR, first we are considering for T of S1 closure. So here I am considering for each positive integer we are constructing open sphere Sn in B. So I can write that in this form. Now B is nothing but union n is equal to 1 to infinity Sn. We know that T is a mapping from B to B prime, which is given in the statement. This is onto and linear, right? So I can write B prime is equal to T of B and T of what is B? B is nothing but union n is equal to 1 to infinity Sn. So I can write this as union n is equal to 1 to infinity T of Sn. This is nothing but B prime. Call this as equation number 2. Okay. So since B and B prime are Banach spaces, we can say that B prime is complete as metric space. Now from Bayer's category theorem, this is you might have studied in your previous semester. From Bayer's category theorem, I can write interior of T of Sm whole closure is not equal to null. So your Bayer's category theorem theory states that a complete metric space is a set of second category. This is what your Bayer's category theorem states. Okay. So now let's see what is first category and what is second category in order to understand this in a better way. So a first category can be defined as if any set, here I will consider a set A, if any set say A can be expressed as a countable union of dense set, countable union of non-dense set, then that particular set is called as first category. Otherwise it will be second category. Okay. So now what is non-dense set? Here we have one more word, that is non-dense set. In order to understand the definition of first category, I should know what is non-dense set. First, what we have done, since B prime is complete as a metric space, using Bayer's category theory, I can write this form. Why? Because Bayer's category theorem states that a complete metric space is a set of second category. So in order to understand what is second category, I should know what is first category. From the definition of first category, I should understand what is non-dense set, right? So now let's see dense set first. A set A is called dense if and only if interior of its closure is equal to null. So if any set is called as dense if its interior of closure set A is equal to null. That means here we are considering a set A. I have to find out A closure. If I take interior of this A closure and if this is equal to null, then you can call that set A as a dense set. Otherwise it will be non-dense set. Okay. So now let's come back to the definition first category. If any set A can be expressed as a countable union of non-dense set, then that set A is called as first category. With a dense set, make a small correction. If interior of A closure is not equal to null, then it is dense set. Okay. If interior of A closure is equal to null, then this is non-dense set. So now compare the definition with first category. If any set A can be expressed as a countable union of non-dense set, that means countable union of null, will come to first category. Since B prime is not null, it will come under second category. Okay. So using Bayer's category theorem, since it is of second category, you can write interior of T of Sm whole closure is not equal to null. Now if interior of T of Sm whole closure is not equal to null means this implies that T of Sm whole closure, it has an interior point, right? I will denote that interior point as y0. So now I can write y0 belongs to T of Sm. Because we know that if I say it has some interior point, y0 belongs to T of Sm whole closure, that is nothing but y0 belongs to T of Sm minus derived set of T of Sm. So obviously y0 belongs to this or this. We have seen this concept in the closed graph theorem, right? So similarly from that I can write that y0 belongs to T of Sm. So now we can construct a mapping from B prime to B. This is a mapping such that here the points are f of y is equal to y minus y0. We are constructing a mapping f from B prime to B such that f of y is equal to y minus y0, which is a homeomorphism. How can you write this? You can understand this in one more way, that is, if y0 is an interior point of this, then there exists an open set, say G, such that your y0 belongs to G and this will be subset of T of Sm whole closure, right? So now operate f on both sides on all the points. So you will be getting f of y0 is a subset of f of G and this is subset of f of T of Sm whole closure. So from this mapping you can write f of y0 as y0 minus y0 and this is subset of f of g into t of Sm whole closure minus y0. Y0 minus y0 is 0. 0 is subset of f of g, and this is subset of t of Sm whole closure minus y0. So from this you can conclude that 0 is a interior point of t of Sm whole closure minus y0. Right? So since G is an open set and F is homeomorphism, f of G is also open. Just check these steps once again. So T of Sm whole closure has an interior point. I have just considered that interior point as y0. Okay. So now we are constructing a map from B prime to B as F such that the elements will be in the form of f of y is equal to y minus y0, which is a homeomorphism. Okay. So now from this there exists an open set G such that I can write y0 belongs to G and it is subset of T of Sm whole closure. So now operate F on both sides. So you will be getting f of y0 subset of f of G subset of f of T of Sm whole closure. Now from this, what is f of y0? I can write it as y0 minus y0. This is subset of f of G. Again f of T of Sm whole closure can be written in this form. So we are getting T of Sm whole closure minus y0. So y0 minus y0 is 0, subset of f of G, subset of T of Sm whole closure minus y0. So from this you can say that T of Sm whole closure minus y0 has the origin as an interior point. Call this statement as your equation number 3. Okay. Now we have to prove that T of Sm minus y0 is a subset of T of S to M. That means we have two open spheres. In this is the radius m. So this inner sphere is denoted as T of Sm. From the center to here it is 2m, and we are denoting the image of this sphere as T of S to M. Okay. We have to prove that T of Sm minus y0 is a subset of T of S to M. In order to prove this, first I will consider y belongs to T of Sm minus y0. If I prove the same point belongs to T of S to M also, then I can say that T of Sm minus y0 is a subset of T of S to M, right? So let us consider this is some arbitrary point. So we are writing y belongs to T of Sm minus y0 be some arbitrary. Then there exists some other point, say x. This is belongs to Sm such that y is equal to T of x minus y0. I am just writing the whole thing in this way. Okay. Now from this again I can write y0 belongs to T of Sm. This implies there exists one more point, say x0, belongs to Sm such that y0 is equal to T of x0. Right? So using this two, I can write y as T of x minus T of x0. Since T is linear, y is equal to T of x minus x0. Call this as equation number 4 and this as equation number 5. So now your x and x naught are coming from Sm only, right? I can write x comma x naught belongs to Sm. So this implies norm x minus x naught is less than 2m. This is diameter of open sphere Sm, right? Diameter of open sphere Sm. If you take the radius, it is m. If you are taking